slides. Can you see my slides okay? Yes? Okay, perfect. All righty. Welcome and good morning, everyone. We're going to go ahead and get started. My name is Caitlin Tucker. I'm with the Partnership for the Delaware Estuary. And I wanted to welcome you today to the Wetland Assessment Tool for Condition and Health, or WATCH workshop. I'd like to start by saying thank you to the National Fish and Wildlife Foundation for their generous support of the project, and to the New Jersey Department of Environmental Protection for early support of the WATCH tool. Just a few quick housekeeping items to review before we get started. Please make sure you can hear us. If not, there are some instructions on the left side of the screen to help with any audio issues. If you'd like to ask a question during today's session, please put any questions into the Q&A box. You can find this icon at the bottom of your screen. You'll be able to see all questions submitted by other attendees, and you can even comment on them as you wish. Lastly, please use the chat box, also found at the bottom of your screen, if you need to get in touch with us about any technology issues or just anything that needs to be brought to our attention. You will be muted for the duration of today's session, so we can unmute you if needed, but we anticipate you will mainly be muted. We are going to stay on time today. We may even finish a few minutes early, so we hope you'll be able to stay for the duration of our session. For today's workshop, we will have a mix of PowerPoint presentations as well as live demonstrations of the WATCH tool. The first half of the workshop will be introductory material geared towards what WATCH is and how it can be used in restoration work. We will have a short break halfway through the session, and then we will continue hearing more about WATCH as well as other tools that can work in tandem with WATCH. So we're really excited to hear more about that. We have 5 speakers today. They are Beatrice O'Hara, Ellie Rothermel, Josh Moody, and Leanne Hoff, all with the Partnership for the Delaware Estuary. We're also excited to have Jordan West from the US EPA Office of Research and Development with us today. I will let the speakers introduce themselves as they wish before their presentations, but just wanted to share all of them with you before we got started. And then lastly, you should have received a copy of the WATCH tool as well as the user guide in emails that I sent around last week. So feel free to follow along with those as you wish during today's presentation. And we really look forward to hearing your feedback and questions. With that, we are going to do a quick poll today. So I'm going to stop sharing. Okay, let's see if I can launch this. Okay, hopefully you can see a poll or two up on your screen. So the first question is, what sector do you represent? And there are a few different options there, including nonprofit, local government, state agency, and others. And then the second question, which I think you can see, allows multiple answers. And it's a question about how much prep did you do for today's meeting? So you read the email that was sent, maybe you watched the YouTube video that was created. If you looked through the user guide, that's great. If you opened WATCH, that's even better. And if you didn't do any of those things, but you're just here, that's just fine as well. We're very glad to have you. So I'll give you all a few minutes to answer those questions, and then we'll do a quick recap before we jump into today's presentations. All right, it looks like most of you have voted. A few more responses are coming in, almost everyone. All righty, I'm going to end the poll and I'm going to share the results with you. So A lot of great coverage of different sectors today. Looks like most folks are from nonprofits, but we also have quite a few from state and federal government as well, which is great. It looks like almost all of you read the email that was sent, so that's good. Hopefully that is how you got here today. But quite a few of you also looked at some of the other resources that we sent around, and a few of you even tried to enter data into Watch. So that's great as well. And we are really glad that you are here today. So thank you so much for joining us and for participating in our icebreaker poll there. I am going to turn it over to our first speaker of the day, Beatrice O'Hara. So Bea, take it away.
Thank you, Caitlin. Great. So you should be seeing my screen now. Again, thank you, Caitlin. Hello, everybody. Thank you for joining our workshop today. We're really pleased to have you here. And from the looks of the poll, it seems like we got a good mix of people from different sectors, and that's also wonderful. Because this is exactly why the Watch project was developed and why the Watch tool was developed, why the Watch project was conceived and why the Watch tool was developed. Not only to help us evaluate the health of our salt marshes, but also to allow us to maybe come to our assessments from a different perspective other than our own area of expertise. And then also to provide standardization across all of our practices as we do our site assessments. So over the next 10 minutes or so, I'm going to take you through an overview of what is Watch, what does it do, how is it different, who are its users, and why it's an important tool to have in restoration work today. So Watch stands for Wetland Assessment Tool for Condition and Health. And basically, this tool is an interactive spreadsheet that forms the framework to provide us, the users, with a comprehensive evaluation of the health and condition of our salt marshes based on key attributes that have been found to be and are accepted as foundational to the basis of a proper salt marsh functioning. So why Watch? Well, as I try to depict from these pictures here, coastal wetlands, and in the case of this workshop, salt marshes, are very complicated systems, right? I mean, they have very convoluted processes that are interconnected, and this can sometimes make it difficult to untangle all of that data to get to the root cause or causes of concern at our site. And since we all can't be experts in everything to do with salt marsh functioning, Watch is here to fill that gap in our toolbox or in our tool belt to provide credence to our evaluations and our projections of salt marsh health through a holistic assessment of key attributes. And a holistic assessment of any system, whether it be ourselves or a salt marsh, is critical to an accurate diagnosis, don't you think? I mean, consider when you go to the doctors or you take your children to the doctors. You expect that that doctor will listen to and evaluate all of your symptoms together, collectively, holistically, if you will, to arrive at a well-informed, comprehensive diagnosis. Well, Watch allows us to perform that same due diligence to a salt marsh site. Okay, so by now you're probably asking yourself, what are these key attributes and what makes Watch so different from all the other tools I already have? Well, those are good questions, valid. Let's take a look. So Watch holistically evaluates 6 key attributes that have been shown to be foundational to the proper functioning of salt marsh. And those are biology community, hydrology, horizontal position, water chemistry, soil condition, and vertical position. We also have a 7th attribute, sedimentation, that's in the works right now, so stay tuned for that at a later date. So for each of these 6 key attributes, the user enters site-specific measured data, current data, user-defined criteria standards that they've gathered either from the reference material or maybe your own long-term monitoring efforts, trajectory metrics, and projected timeframes. And then Watch takes all of these and assesses them in a holistic framework. Watch looks for current and future violations where the criteria standards are not met, and combinations of those violations that may also indicate a deficiency across the salt marsh site as a whole, and then delivers to us a summary of these violations, the deficiencies, and any other attributes of concern, both today and into the future. So, oh, sorry, let me go back. So it is this holistic approach that Watch takes, looking across all these attributes of specific attributes and specific combinations of attribute violations that sets Watch apart from other tools. Now, this is a very simple explanation, I understand, but Ellie is going to take you through a more in-depth look at the Watch tool in just a few minutes. So in the Delaware Estuary and in Barnegat Bay, we're lucky to have a variety of long-term monitoring data for some of these attributes that we have gathered through the Mid-Atlantic Coastal Wetland Assessment Program, otherwise known as MACWA. And if you're interested in any of these data sets, you can contact Leanne Hoff or really anyone on this workshop, and we can point you in the right direction. So is Watch for me? You betcha. Although users can't be totally unfamiliar with salt marsh ecology, the tool does require a certain degree of salt marsh understanding because it directs the user to enter metrics and standards that go along with these key attributes. However, users equipped with sound knowledge of salt marsh functioning and a little bit of resourcefulness can gather data from other long-term monitoring efforts, from the outputs of other tools possibly, or even the academic literature. But I'm betting the fact that you're here today means that you're already involved in salt marsh ecology in one form or another and already familiar with those metrics and standards within the Watch tool, and they will be very familiar to you. And I think that you will find Watch not only intuitive, but flexible and robust. So here is our little Watch guy again, and he's looking at these two different salt marsh sites. And land managers and practitioners and restoration practitioners can use Watch as a guide to identify issues at the site level and then also compare issues across sites like Watchy is doing in order to prioritize your intervention tactics, timeline, timeframes, and also to manage your budgets. And as most of you know, all of us are working within constraining budgets and timelines. So Watch can help us by helping us to, kind of laser focus our resources objectively through data-driven results. And that's exactly why Watch is important in restorative work, because it is data-driven. There isn't any guesswork here. It evaluates the attribute data collectively to provide us with a summary of violations, deficiencies, and attributes of concern across our site, and therefore it subtracts any subjectivity that we may bring to our assessment due to our individual areas of expertise. Watch also provides standardization and repeatable and reliable processes so that no matter what your area of expertise, we're all talking the same talk and walking the same walk. And since this tool aligns with other monitoring guidelines that many of you are already probably using or are familiar with, such as the framework for developing monitoring plans in coastal wetland restoration and living shoreline projects in New Jersey and Delaware, the Watch tools should feel very familiar to you. And finally, Watch also has an area to document your decision-making processes as you move through the tool. So in this fashion, not only the tool, but your data, your standards, your thought processes, all of these can be documented and communicated with your team or your partners so that everyone's kept in the loop, on track, and hopefully on budget. So that about wraps up my overview of Watch. I think we'll probably look to see if there's any questions or comments in the chat, so I'll throw it back to Caitlin.
Thanks so much, Bea. Just a friendly reminder to everyone, feel free to ask questions in the Q&A box and we will try to get to as many as we can. Bea, there is a question, and I will say any of the panelists can answer this. The question is, you mentioned that sedimentation is to be added, which is an important input. What will be the input parameter for that? Is it turbidity or is it something else?
Yeah, so I'm going to throw that over to Josh or Leanne to answer, because I do not have that answer.
Sure, no problem. Any
It's
panelist
doing the
can
work.
answer.
Yeah, I think I can take a quick answer there. So as we start to look at watch and go through some of the tabs, you're going to notice for each of these attributes, there's, for some of them, there's more or less different metrics that can be utilized to look at that. We actually formed a sedimentation tech group that we're going to be working with over the next year to sort of hone in on which metrics and which methods we're going to try to integrate into watch to best capture the sedimentation component, but also integrate that component with the vertical position and the hydrology attributes as well. So it's sort of a two-step process, and the metrics that'll be chosen are going to have to be considered along with how that attribute will integrate with the others.
Awesome. Thanks,
Thank you.
Josh. There is one other question, which I think we're going to get into in the next presentation. The question is, where did the terms violations and deficiencies originate? And we can hold, Ellie, if you think it's best just to go through your presentation.
Yeah, I'm not sure if my presentation will give a direct answer to this question, but I think it helps clarify some of the differences between those two terms, and it might help it all make a little bit more sense.
Yeah, I agree.
Maybe I should go through my presentation and we can see, we can just discuss that further, maybe at the end of this session. So
Okay.
It is a valid question, I think.
Yeah, and I think, like you said, your presentation will provide some context for that, which will be great, and some of the other terms that are used. So with that, Ellie, I think we can go ahead and start your presentation. Take it away.
Thanks, Caitlin. So today I'm going to go through more of an introduction and walkthrough of the watch tool itself. And thanks again to Bea for that great overview of the tool and why it exists. That was really great. So just a brief outline of what I'm going to talk about today. First, I'm going to go over some of the foundational terms and connections that are underlying the watch tool. And then I'm going to review those attributes that Bea already kind of outlined before and talk about how they're used in watch. And finally, I'll walk you through the actual relationships and outcomes between these different terms and connections in a bit of a tool workflow. So first, going into our key definitions and connections within watch. These definitions are really going to be essential in how we describe going about assessing wetland condition and health. So first things first, we need to define the essential features of a salt marsh, the features that we know are key to wetland functioning. And here we're going to call these our site attributes. So then what we need next is a way to describe and to measure these attributes. We're going to measure our features using relevant metrics and associated established scientific methods. So these tell us how to look at a site, but then how do we actually move toward an assessment of how our salt marsh is doing? Well, what we need to do is take our current value for each attribute that, of course, we've calculated using an appropriate metric and method. And we need to ask how this current value compares to other similar sites and also how it might fare into the future. For the purposes of watch, we're going to answer these questions by comparing the current value to both a criteria standard and to a trajectory. This criteria standard is going to provide a reference for our current value, and the trajectory is going to help us predict what the current value will look like at some future point in time. Then to reach the final step in our condition and health assessment, needed to compare our current value, criteria standard, and trajectory, and we ask, do we need to be concerned about our site, either now or later? The watch tool is going to answer this question by identifying site deficiencies and telling us which attributes might warrant further investigation. And I'm going to go into these relationships in more details in just a bit, But essentially, we can look at these in medical terms, going back to that doctor visit analogy that B kind of discussed earlier. We can think of these as if our salt marsh were taking a visit to the doctor. So our use of defined attributes and methods to get measurable metrics gives us an evaluation of the site characteristics, like a doctor might do by making measurements of your weight or blood pressure, for instance. Then by comparing that current value from our evaluation to a criteria standard, this allows us to get a diagnosis of site condition and health. And this would be like a doctor determining your health by comparing your weight and blood pressure to other adults in a similar age and height range. Finally, the trajectory and identified deficiencies represent our prognosis of the site, or how we expect the condition of the site to progress into the future. Here, WATCH will provide the likely course of wetland functioning, like your doctor might identify the level of concern for your overall health, given your current projected lifestyle choices. So this covers our basic definitions and their relationships within WATCH. But now I'm going to go through a more in-depth look at the attributes that B covered earlier and the metrics and methods that we use to describe them. So these 6 attributes are the key measurable features of a salt marsh. And the 6 attributes highlighted here have been identified as fundamental in nature to proper and resilient salt marsh function. We chose these through a systematic review and consultation with wetland restoration practitioner partners. And the key to describing these attributes is really ensuring that they're applicable is to use the best and most scientifically appropriate metrics. And on top of that, we need to make sure that we're using the right methods to gather our metrics, so the attributes of our study site can be compared to other similar sites. So for instance, if we look at just one attribute, such as vertical position, a common way to assess this would be to look at elevation. So our metric here is elevation in a unit such as meters. And a common method for gathering this data might be something like LiDAR or an RTK GPS survey. And in fact, all of the WATCH metrics and methods align with the techniques that have been outlined in both Delaware and New Jersey state monitoring plans. Now, in addition to this, all of these metrics and methods require justification within the WATCH tool. And these justifications allow reviewers to understand user-based data decisions, and they provide transparency throughout the WATCH evaluation process. Now, delving further into these 6 attributes used by the tool, as I've already covered, we have vertical position. And those are the features that describe, relate to, or influence elevation. And Josh is going to go into this further a little bit later, but the tool does incorporate sea level rise for assessment of this attribute. Next, we have horizontal position, which are the lateral aspects of a feature of interest, such as a waterward edge or a continuous vegetation line. And like vertical position, this would likely be measured by satellite or RTK. The biology describes the living community of the site and can be defined by a variety of metrics. For instance, vegetation productivity, presence of a certain habitat, or abundance of specific flora and fauna of interest. Next, we have hydrology, which indicates how water moves in relation to site features and includes metrics like tidal restriction and drainage. Soil condition then are those qualities related to the substrate or sediment characteristics of a site, essentially the underlying landscape of a marsh, like its soil type or its decomposition state. Finally, our water chemistry describes the water quality of the surrounding water body, which can be looked at in terms of salinity, phytoplankton, or dissolved oxygen concentrations, for example. So now that we understand our fundamental marsh attributes, I'm going to take you through a more in-depth walkthrough of what you put into WATCH, how WATCH assesses these inputs, and what you get out of WATCH. So as I've described, we have our 6 fundamental attributes laid out here. And for each of these, we're going to input some data. First, we have our current or most recent metric that, as I've described, is measuring using an appropriate metric and method. This tells WATCH what is the current state of our site. We then compare the state to a known criteria standard, which is essentially a set reference value for our salt marsh. And this can come in multiple forms, either as a quality criteria, which is gathered from the literature and is an optimal published standard, a reference criteria, which is gathered from similar representative salt marsh sites, or a target criteria, which is a user-defined specific metric value range that is desired. So with our criteria metric, WATCH is told what is an appropriate quality, reference, or target standard for the site. Our next input is a trajectory, which represents the best scientific evidence of a rate of change for a given metric. And this is entered as a metric trajectory range, and it's in the same units as the current value and the criteria standard. Now, along with this trajectory, we also input a number of forecast years, so that together the trajectory and forecasted time frame tell us what is the current rate of change at the site and how many years into the future are we forecasting. Now, like the current value, each attribute, criteria, trajectory, and forecast timeframe is going to require that the user provide justification for that choice of data input. In fact, Watch will not calculate any output without these noted justifications. This really allows for maximum transparency and transferability throughout the tool assessment process. So with these inputs covered, Watch is then able to make calculations to provide an informed and holistic output. To give clear answers, the tool calculates and flags violations and then determines deficiencies. To take you through this a bit, here violations indicate where the current or projected state of the attribute currently lies outside the acceptable bound that the user has defined. These violations can come in the form of current violations, trajectory violations, and different combination of these will lead to overall attribute violations. Watch then looks at these and determines overall site deficiencies or the total level of concern for the site. And Watch will make final outputs that describe the site status as either deficiency detected, further evaluation recommended, or no deficiency detected. So to take you through this process of calculations and outputs a bit further, first for our calculations, Watch will compare the current metric and the criteria metric and ask, is there a problem today? And if there is, Watch will flag a current violation. Watch will also compare the current metric, the trajectory metric, and the forecasted time frame to ask what the value will be in the future, giving us a forecasted or projected metric. Comparing this to our criteria standard, we'll then ask, is there going to be a problem tomorrow? And again, Watch will flag this as a trajectory violation if it does occur. The criteria metric is also used to inform some large-scale context questions. Here, attributes may have some diminished function that could be a concern when combined with other current or trajectory violations. Finally, Watch will provide outputs given our calculations. And here, this will be in the form of both an attribute status and an overall site status. Here, different combinations of violations will actually lead to an overall attribute status being flagged as violated depending on the attribute. For instance, a horizontal position violation, either currently or in a trajectory violation, will automatically be flagged as an attribute status violation. However, other attributes such as vertical position, hydrology, or biology will need a trajectory violation in order to be flagged as an overall attribute violation. Finally, soil condition and water chemistry can also receive violations for not meeting the desired criteria, but they will not contribute to the next step in the process, which is the identification of our site-wide deficiencies. So if none of your attributes are violated and none of these are detected, then Watch will come up with an overall output site status of no deficiency detected. However, if there is a violation of the horizontal position or two or more violations for vertical position, hydrology, and biology attribute combinations, then Watch will determine that there is a site-wide deficiency detected. However, if you have different combinations of attribute violations which are present but don't show enough evidence to trigger a full site-wide deficiency, Watch will give a site status of further evaluation recommended. And it will actually provide a list of attributes that might deserve increased monitoring focus moving forward. So just to summarize all of this, essentially what Watch is doing is it's integrating multiple data inputs and using these to give to the user a holistic weight of evidence regarding site deficiency, both currently and into the future. And next up, Josh will be leading you through an in-depth look at some of the unique features of Watch. So with that, I will hand it over to Josh to actually take you through some aspects of the tool itself.
Okay, thank you, Ellie. All right, so as we get started here, I'm going to provide a quick review of some of the things Ellie just went over. I know it can be a lot to take in all at once, but I think that was a pretty thorough review of how these processes work. So we'll do a quick review of the take home, and then what we're going to do is actually hop into Watch for just a second. I'm going to go through all of the different tabs, show you what's inside each of them, how they work together, and go through the outputs as well as some of the additional features. A little later on in the webinar, we will get into how we interpret those outputs. You know, what do certain combinations mean to us? You know, how can we draw conclusions from the outputs? So just a few things to remember to start with. You know, the goals of Watch. And the goals of Watch are really to facilitate a few different things. You know, the first is really a holistic understanding of the site. You know, as both B and Ellie brought up, you know, salt marshes are complex environments. There's all these interactions going on, and we all as investigators come from our own particular perspectives. So we tend to evaluate things through that lens. And so one of these purposes of Watch is to help remove us from our bubble a little bit, to consider the wider array of influences that could be affecting our site. And this can ultimately lead to better team building and a more comprehensive evaluation. It can also provide us with a common language for discussion around these complex topics. You know, if we come up with some outputs that we don't know how to fully interpret, you know, having something like Watch where our data is organized or justifications are organized, those can help facilitate conversations in the next stages. The second thing to remember is, you know, Watch starts out assuming no deficiency. You know, we take sort of a philosophical hypothesis testing approach to this. There's no deficiency assumed, and the deficiency is determined by the weight of the evidence that you provide to the tool. So really the burden is on the user in Watch to be providing the tool with the right types of data, the most representative types of data, in order to make those evaluations. And that's something we're going to talk a little more explicitly about later. The third is the justifications that are required for calculation. And this is really to help provide us, you know, with tracking how we're thinking about projects, and especially with long-term projects. I mean, I always think I'm going to remember why I made certain decisions or where I sourced certain data from, but, you know, 5 years down the road in a project, it's nice to have that place where you can go back and reflect on the history of the decisions, the history of the data that we use. And then the attribute violation. So a quick review of those. You know, an attribute can receive a violation in the horizontal from either a current or a trajectory violation. The vertical, bio, and hydro attributes require a trajectory, but if you do not have trajectory data and do not fill out the trajectory portion, you can receive a violation for a current criteria violation. But with trajectory data, you know, becoming more and more accessible to us, it's highly recommended to source trajectory data when available. And soil condition and water chemistry, these are really our global attributes here. So they can receive violations, but they don't trigger deficiencies, and they're really there to help us contextualize some of the output. And we're going to discuss that a little bit later as well. So right now we're going to go into Watch and take a look at what is included in the tool. So the first thing you'll see is along the bottom, we have a series of tabs. The first tab is our instructions tab. So a user guide was provided with Watch, but you know, it's not always you know, easy to flip through a user guide where you're trying to use a specific tool. So we've included an instructions tab here for to flip back and forth between, which includes a lot of the basics. Some of the definitions are described here, output summary, what you're going to get out of it. an overview of what each of the different tabs looks like, and then procedure for entering data. So these are set up in a stepwise procedure with a few notes, and we also have points of contact here as well. The second tab is what we're calling a regulatory checklist. So these checklists are not comprehensive for each of the permits represented, but we worked with regulators from Delaware and New Jersey to identify some of the key items in certain permits that actually align with some of the metrics evaluations you might be performing in Watch. So permits represented on this page are New Jersey DEP's 24 and creation, restoration, enhancement of coastal wetlands, Army Corps nationwide permits 13, 27, and 54, and DNREC subaqueous lands permit. Now, again, the list of requirements here is not comprehensive, but if someone is going to evaluate a site and they think that they may, if there's evidence there, want to go in and perform some types of intervention, and they think that type of intervention effort would require certain permits, what they can do is try to start compiling some of the information they would need for a permit application while they're performing some of the evaluations in Watch. So what the user can do is select a permit here, and on our output reflection tab, it'll be highlighted that you have selected it and whether it's complete or not. And then the list of the noted requirements and their metric alignments are here and available. So if thinking about the lateral shoreline change at my site, if I'm going to need to provide the position of the 77th tide line, while I'm evaluating that lateral shoreline change, I can start to put that information together. And for some of these requirements, we do have resources in the last column here where you can go to compile some of that information. Additionally, proposed vegetation communities, understanding what type of vegetation might be across the entire site. This would align well with under the biological attribute of vegetation productivity metrics. And then there's a little bit of additional information to help quantify what we would be looking for in Watch, as well as what a regulator might be looking for in terms of the application. So if you were interested in GP24, you could select that. And as you start putting these materials together, you can start checking off some of these boxes. And as you complete attending to each one of the items from that permit that aligns with Watch investigation, and you complete that, that will be noted here on the output reflection tab. So the next series of tabs are the different attribute tabs. We have our horizontal position, vertical position, biology, hydrology, soil condition, and water chemistry. Now we're going to go through each of these tabs a little bit later when we talk about interpretation, but we'll take a quick tour of one of them. We'll start with vertical position. So each of the tabs generally looks the same, and it follows the outline on the instructions tab here, where first we have a metric and a method. Now, for vertical position, we're really looking at elevation. So we don't have many metric choices here, but we do have different method choices as well for documentation purposes. Then we have a spot here to input our current value. And so for this example, we're just going to use some easy numbers just to walk through this. And our current value would be, let's say it's 1 meter. Now here's the first of the sets of justifications. In each one of these tabs, you are asked to fill out why you have selected that. And again, that's for your own reference. It's for other people reviewing this, passing a project on to something else. Is to keep a good history of why the different decisions were made for all the different data choices that were that had to be made during the evaluation process. So you input your current metric, its units, and its justification. Units do need to be consistent across the across each attribute. We'll take a look at what happens if they're not when we get to the end here. Then we put in our criteria values. So for this example, we'll just say we want our marsh platform elevation to be between 0 and 2. We make sure our units align. We can choose the type of criteria here. Is this quality? Is this sourced from the literature? Is it reference? Is it something we know about the local area that we want to match and compare against? Or is it a specific target, like say 0 erosion rate, something like that? And our justification for where we got this information. This was a reported growth range in a paper. Next, we put in our trajectory information. So maybe this data comes from the means of 3 nearby sets locations, and we see that there's actually a decline in elevation somewhere between 1 and 5 millimeters per year. Now, it's important to notice that whenever we have a decline, erosion, reducing elevation, it is important to add a negative sign in here, because as WASH starts calculating things, anything that's growth positive is going to be considered growth, and anything that's going to be a decline has to be represented negatively. And then we enter our forecasted time frame. Here, we're going to say 10 years, and maybe that's because we're starting to plan out a budget for the next 10 years, and we want to make sure and see if we need to set money aside for any work here. So then WASH is going to start doing some calculations, but first we're going to discuss the sea level rise component here. So I'm going to hop back here for just a second and discuss the vertical position in terms of sea level rise. So for each one of the metrics, we're really looking at the 3 states that Ellie outlined: the current state, the rate of change, and the predicted state. So for vertical position, we have a current elevation, we have that criteria we want it to be in. So let's take an elevation range of 0 to 4, nondescript units. And our current elevation is A2. And we want that elevation to be between 1 and 3. So in vertical position, we have 2 types of rates of change we're looking at. We're looking at an elevation trajectory, how that current elevation is going to change. But then we also have sea level rise. So our elevation trajectory is going to interact with our current elevation. What do we expect that elevation to be at some point in the future? But sea level rise is going to adjust our criteria range. So if we think about it in terms of rising waters, if we want to be at some position NAVD 88, because of tidal inundation, as sea level rise, the criteria that are the range that we want our metric to be within is going to change at the same rate. And so this is going to lead to our predicted state. So our projected elevation is going to decline by half a unit here down to 1.5. And then our projected criteria range is going to move up 1 unit from 1 to 3, now up to 2 to 4. So back to our example here, we can put in our sea level rise rate. Let's just say it's 5 millimeters. And then it's going to calculate our forecasted criteria. Now, getting the units, keeping the units the same is always important. So let's say we weren't thinking about this and we just put in millimeters. What WASH is going to provide is this going to provide a place for error notes at the end there. So we want to make sure our units are the same. And again, say we did not add a justification here, we are going to get a note at the end that there is no justification in that column. So what do we see with this outcome? So our original metric elevation was 1 meter. The mild elevation change after 10 years is going to show a decline of 1 to 5 centimeters. And so our original criteria range was 0 to 2 meters. Modeled after 10 years of sea level rise is going to be adjusted by 5 centimeters. And what we see is our predicted elevation is within the bounds of our forecasted criteria. And therefore, we are not going to see or receive a current violation or a trajectory violation. And therefore, our attribute status is not going to receive a violation either. So we'll touch on the horizontal position, bio, hydro, and soil condition attributes in the next section. But just to walk through the last couple of tabs, what we're going to receive in our output summary tabs, the data is going to be compiled in a couple different ways. So any of the combinations of metrics, either horizontal position or two or more of the vertical biology or hydrology attributes that receive violations will indicate a site-wide deficiency detected. And those will be noted here with an X in the cell. But any other attributes that might receive a violation, but that aren't related to any of the site-wide deficiency detected will also be noted here. So something like soil condition, which will not contribute to the deficiency detected, might receive a violation and therefore would be noted here. And we also provide the associated attributes. So associated attributes are attributes that have been known to be closely associated with the conditions in this. So maybe you just go out and evaluate, you evaluate one attribute, you evaluate the biological attribute, and you receive a violation for it. Well, what Watch is going to tell you is that it can't give you a full deficiency detected for that singular violation, but it would recommend that you also look at vertical position and hydrology that are closely related to that. These combinations of deficiencies and attributes of concern are summarized in a table at the bottom as well. And we'll go through that a little bit more when we look at how to interpret the data. But the last tab I want to walk through is this output reflection. And this is a little less data driven, but it's going to provide a little bit of guidance on how we can interpret some of the data we get. So it has a list of interpretive guidance here where there's discussion on certain topics about, idealized versus acceptable conditions. Are you selecting appropriate criteria standard ranges? If you reflected near a narrow range, it might be easier to violate that. And is that really an appropriate range of values to choose from? Or, using elevation ranges of data that might be from a site that's not necessarily comparable to your site. Investigating the temporal component, looking at these trajectory timeframes, is the violation dire or not? And thinking about the importance of trajectories, and really, again, are we using the appropriate reference sites? Also in Watch, you can take a multi-metric approach. You can evaluate a variety of different metrics for each attribute to compare the outputs to see how they fare next to each other. And then you can look for relationships among those outputs with some of the different attributes as well. So there's some dialogue presented here to help walk through some of those common questions that come up. And actually, quite a few of these questions we're going to go through when we do the interpretation exercise a little later. There's also a series of regulatory considerations that we developed along with regulators in New Jersey and Delaware that outside of evaluation of your site, things that people need to have considered or be aware of if they're thinking about performing some type of intervention, things such as habitat trade-offs, things about fill considerations, developing adaptive management and monitoring plans, putting together items that characterize your site overall to show the understanding that you really have a good idea of what's happening holistically across your site. And to go back to something I said, towards the beginning, and that's really one of the primary goals of Watch, not only to just understand how these different attributes are performing and looking at them together, but to really get a big picture understanding of our site and how that site is changing over time, and what us as practitioners going in and starting to perform changes to those sites, what that might mean and what we need to consider in beginning some of those efforts. So I think with that, I'm going to turn it back to Caitlin. We may have a couple of questions. And then next we'll be getting into some real world example with Leanne, and then getting back to some of these interpretation and additional tool alignments.
Thanks, Josh. Some of you may have noticed Leanne was answering a few of the questions during the presentations. One I did just want to draw some attention to. There was a question about if the Watch tool could be used outside of New Jersey and Delaware in terms of geography? And the answer is yes, the tool is not location specific, so it can be used in other states that have tidal marshes. And then we do have some other questions that aren't answered yet, Josh. So the first one is there a drop down for measurement justification? So maybe you can talk a little bit about the drop downs that are available.
Sure. So the drop downs in the tool, it's not for the justifications. The justifications are open cells where, you know, it's really hard to have a drop down for one of those because data and reasoning could you know, there could be a lot of variety across users. And it's really there, you know, for the user's benefit to really catalog, you know, all of the decisions. So we left those open. When we say that, you know, Watch will not calculate without them, you know, those boxes do need to get filled out. So it reminds people to go back to them, but ultimately it's really on the user to decide what they want to put in there, what they think is going to be beneficial to them in the future. So there is not a drop down for those.
Okay, great. And then the second question, is it correct to assume a linear trajectory rate of marsh platform change?
Well, I see Leanne mentioned that she was going to answer
Yeah,
that question. Leanne, do you want to hop on?
Sure. I think that the short answer would be yes. There's a lot of models out there that do suggest that the marsh platform response to sea level rise will be nonlinear. But that's probably over longer periods of time, you know, greater than a decade or so, or maybe even more than that. Most of our monitoring data, the best monitoring data that we have about platform elevation changes, most of it looks to be reasonably linear over the time period that we have been monitoring. So that comes from like surface elevation tables and things like that. You know, data sets that are, you know, less than 15 years, we usually analyze them with linear models. So short answer is yes.
And then one final question is this tool applicable for urban shorelines and retrofit areas?
Yeah, that's a really good question as well. And actually, you know, this gets at some of the current activities that we're doing with Watch, and actually some of the feedback that we're going to be hoping to get from all of you now and in the future. So I'll talk a little later about where we're at in this state, but in addition to adding the sedimentation attribute, we're also going to be doing field validations at a variety of different sites. So, you know, with Watch, it's one of those things where it's a very plastic tool where the burden is really on the user to provide certain types of information that it's appropriate for Watch to evaluate. So, you know, whether it's always applicable in one place or in one sense, you know, is something that we really want to explore more. So as part of this field validation process, you know, we're going to try to be looking for a bunch of locations that span a wide variety of condition, you know, upland condition and restoration condition and potential, you know, observable issues. So thinking about shorelines and marshes that are in more urban areas is definitely a consideration as we start to move into this validation phase. And if anyone here has sites that they would like to nominate as validation sites for that process, which will likely begin this summer, please feel free to email them to Leanne, Ellie, or myself, and you know, we'll be in touch.
Awesome, thanks, Josh. I'll throw those emails into the chat box in case anyone doesn't have them. One final question that just came in. And Leanne, this one may go to you. The question is, how do trajectories for vertical position work without set data?
I mean, I think that that's license for you to get creative. If you have really good LiDAR over 2 time points, that's usable. If you have other really great elevation surveys, as long as you have 2 time points with good quality data, I think that you can get those trajectories.
Awesome. Thanks, Leanne. And then one final question. These questions are great, everyone. Thank you for submitting them. Is this approach applicable to tidal freshwater marshes as well?
Yeah. So, you know, there's a lot of talk in tool development in the Delaware estuary now about, you know, there's a lot of focus on salt marshes, and there's a lot of increasing interest in the right places in the freshwater prism, as there should be. And so how do we, is there transferability, you know, among some of these tools? So watch the relationships that are built into watch from which the calculations are made and which the violations and deficiencies are specific to salt marsh literature. Right. So the idea going into this was, you know, to develop sort of this plastic framework that would be flexible enough to accommodate a variety of different sites. Now, there's a lot of salt marsh work groups in this area. So approaching the salt marsh platform first was sort of the low hanging fruit. Can we develop this for a salt marsh environment? Now, evaluating its potential transferability is going to require a review of the different interactions and how they work together. So that is something, you know, that is certainly on the horizon and something that's certainly been discussed. But this particular version of watch, I would say its relationships are more reflective of a salt marsh environment. Now, that's not to say during this validation process, since we have so many long-term freshwater stations, maybe we won't play around with it a little bit and see really what the black boxes are that need to be refined to enhance that transferability. But right now it is called out as a salt marsh.
Thanks, Josh. And one of our later speakers may cover tools that may work for freshwater marshes as well. So stay tuned for more on that. One final question, and then we'll go to the next presentation. Is horizontal position a distance or an area? Thinking about marsh migration potential.
You go ahead, Josh.
If you want to feel that was, I think what I would say right now, like when I'm going to go through a horizontal position example in just a little bit. And in that one, I use it as a distance, but it's a distance that's been averaged over space. Now, watch will work as long as all of your units align. And again, this is sort of a framework for people to evaluate their own data. So, you know, I think I've primarily used horizontal position as the position of an edge. So it is a distance. It's not necessarily an area, but that's an interesting question to look into to see, you know, how we would theoretically conceptualize this and if the same sort of relationship across an area would work across a singular distance. So I think I'm gonna have to leave. I think my answer would be possibly, but I usually just use a singular distance. Leanne?
That's what I was going to say. Yeah, I think that the tool is flexible enough to accommodate, you know, slightly different metrics in that capacity. So I don't think the area would be too far off from a distance if that's what, you know, the user wanted to use.
Awesome. Thanks, everyone. We are going to move on to the next presentation. So Leanne's going to walk through a real world example of using watch. So Leanne, I'll hand it over to you.
Thank you, Caitlin. All right, so I am Leanne. I'm the wetland coordinator for the Partnership for the Delaware Estuary. And like Caitlin said, I'm going to be walking through this real world example that I came up with. Oh, I think I'm on automatic slide. So let's do this. So how do we approach using watch? I think the best way to go about this is to you know, practice with these examples that we give you in the user guide. And if you haven't done it yet, highly recommend that you go through those and just see how it works for you using those examples and try plugging in what you can. And you know, let's serve this as a reminder that we do have breakout sessions later today that if you do run through them, you know, we'll have an opportunity to discuss any challenges that you faced. Or you know, maybe adjustments that we can make in the future to make it more usable. And the second piece of advice I always have is to take things one step at a time. Like B said earlier, you know, these are complex systems. So isolating different components, different pieces of data and running it through the tool, you know, one at a time should help sort of conceptualize what the story is at each marsh that you're working in. So again, tidal marsh systems are complex. This is a pretty popular graphic out of USGS that just shows all the different things that could possibly contribute to salt marsh function. Admittedly, the watch tool might be a little bit of an oversimplification because there are so many things, but I think that we did a really good job of creating those broad attribute categories that capture quite a number of these different components. And importantly, because there's a lot of complexity, that means that each site that we encounter is going to be unique. So we are going to have differences among sites, and the user is going to know that site the best. And so that's why it's important, those justification cells that we have to really go through and use those as notes to yourself and sort of categorize why you're doing what and where, because it's you that know the site best. And just to exemplify that, I took these pictures last year. I think they really showcase what I mean. Oh. So this is what looks to be a pretty good functioning salt marsh. We have a dense carpet of spartina alternative flora in the foreground. We may have some frag and snags in the back, but overall we don't see a lot of open water or bare mud or anything like that. But right across the street, and by street I mean dirt road, we have this area, which is in stark contrast to the other side of the street, where here we have snags right in the foreground. We have bare mud. We have a bunch of frag. There is a little bit of spartina alternative flora there, but you can see that this mud is dry. There's something hydrological probably going on here, and that's a big difference, and that's a big difference in a small space. So the watch tool output for this site is going to look completely different than the previous picture, in this marsh. And that's something that I think is important to remember, that the scale of these things can change wildly. But hopefully, by being communicative about, our study area and the things that we're putting into the watch tool, we can begin sort of being more organized about how we're assessing the vulnerability of these areas. So how do we actually approach using the watch tool? I like to split this up into two different sections. What we know about the site, which we can translate to any on-the-ground data that we have, and then what we need for the site, which can be translated into sort of like an ecological goal. What do we hope to attain at that site? And this is just a super simple flow chart that takes us through looking at evaluation. So that's what we're attempting to do here, compare on-the-site data with any reference data that we have. And then we split that into those two groups of what we need and then what we know. And for the watch tool, the terminology splits out so that what we need is our reference data, and those are criteria in the tool. And then what we know that on the site data becomes the values that we put into the tool. And hopefully by using the tool, we can get to that determination of impairments. So in terms of going about what we actually need, this is my go-to here. I go straight to NOAA tides and currents and pull those data. And again, Josh did show you the regulatory checklist in the tool. There are some, there's a column there for links that take you to things like the data resources like this. But this is definitely my go-to. This is the first thing I pull up. The second thing that I did use for this real world example is the USGS CONED topo bathing. So this is a digital elevation model created from LiDAR. And it's pretty thorough. I like it because it does, transition smoothly from, land sort of into the bathymetrical, which is nice in tidal marsh areas, because you can definitely get some gaps there. So I pulled this for our site. And then I also, use MAQUA data that B sort of mentioned earlier, the Mid-Atlantic Coastal Wetland Assessment. We do have long-term monitoring stations out there. At the site that I chose to run this real-world example, we do have a surface elevation table that I was able to pull data from so that we can get that trajectory information. And lastly, it's always good to comb through the literature to figure out what things are already known or what things have already been discussed about things. And so for this example, these are three main pieces of literature that I pulled just to have a background understanding of what's going on. And these are really good papers. So if you don't have them, or if you don't have access, I think that, shoot an email and we'll see what we can do. All right, so for a real world example, we're going to look through different lenses, but in this case, we're going to actually look through the lens of a salt marsh sparrow. And what we're going to ask is, are there any observable impairments to salt marsh sparrow breeding habitat at Dennis Creek? Dennis Creek I chose because it's one of my favorite salt marsh sites. So just a little bit of background. Salt marsh sparrows are salt marsh obligates. They do require higher marsh to be able to nest successfully. And anything less than high marsh, anything lower in elevation than that tends to get too flooded for them to reproduce successfully. So that's going to be a problem. So we're going to sort of focus our watch example around that idea. So just in stating our concern, we're really concerned about decreasing habitat, breeding habitat suitability at this site. And again, this is Dennis Creek, which is in Cape May County, and this orange block is just sort of our overall study site. So vertical position, what do we know? So what I did here was I pulled the LiDAR data from the CONED topo baby, and I just outlined my rough study area, and I came up with a median elevation from that LiDAR, which came out to be 0.804 meters NAVD88. So when we put that into the watch tool, like Josh showed, here is our vertical position tab. I chose that's our marsh platform elevation. The method is LiDAR. There's the value that I just figured out, which is the median in meters. And then there's our simple measurement justification. It doesn't have to be complicated. And that's what I did. That's the median elevation from LiDAR. So for vertical position, this is going to be our trajectory information. So I found that elevation change is approximately 1 to 2 millimeters per year at that site. And that's from the surface elevation table data from our long-term mock web monitoring. And again, vertical position tab in the tool, and converted those millimeters per year into meters per year, which comes out to 0.001 to 0.002 meters per year. And again, simple justification, just the rate from nearby set. So now when it comes to reference data or setting our criteria, this is a little bit more a creative process. So what I decided to do was, establish a quality criteria. And I chose 0.8 to 1 meter NAVD88. And I did that because I presume that's the possible range of high marsh for this site based off of the mean high water value at the Cape May tidal station, which is about 0.74. So that's, plus or minus the standard error, just to buffer it on the lower end. And then the 1 meter NAVD88 is, the upland threshold. So anything more than 1 meter, we're working in upland at that point. So we really don't want elevations to go beyond that. And we really don't want elevations to go beyond that 0.8 meter NAVD88, because that's going to get us out of that high marsh zone. So again, back to the tool, we're inputting our criteria here at 0.8 to 1 meter. We're going to use that quality criteria. And then again, simple justification. I pulled that information from LiDAR, the tidal datum at the site, and then I also referenced a piece of literature here. And as we move through this, we have our trajectory rate in there, and now we're going to input our forecast. So I chose 10 years for this projection, just because I don't feel overly confident in projecting anything more than 10 years for this, especially since we only have 7 years of set data at the site. And that's just what I use for my justification there. And again, the tool automatically computes out those projected metrics for you. So our new metrics are, my thing is covering that. Our low and high values become 0.814 and 0.824 meters NAVD88. So that's our projection somewhere in the next 10 years. So next we're going to input that sea level rise information. So again, that's just from the Cape May tidal station, converted into meters per year. It's approximately 0.005 millimeters or 0.005 meters per year. And then the tool automatically calculates out your new criteria with which you're going to compare your forecasted metrics to, or forecasted metrics to. So our new criteria that used to be 0.8 to 1 now becomes 0.85 to 1.05 meters NAVD88. So our next attribute that we're going to look at quickly is just biology. And what I did here is I just binned the LiDAR into high and low marsh using 0.75 as a cutoff. So anything lower than 0.75 would be our low marsh. Anything higher than 0.75 is going to be our high marsh. And just doing a simple percentage, that comes out to be approximately 57% of this area is high marsh. And going into the tool, again, starting with metric, it's habitat. Our method was percent habitat, 57% being our current metric. And then our measurement justification simply is any marsh above 0.75, we're going to categorize that as high marsh. And for this, I actually chose a target criteria just to show something a little bit different. We really don't have any reference for this outside of what we really want to see. And I chose 40 to 60% for that because our goal is gonna be to have at least half of the marsh high marsh habitat. Because anything less than that, we're bordering on it not being enough habitat for sparrow breeding. And anything less, anything higher than 60% is not habitat mosaic. So we're going to aim for that 40 to 60%. And again, jumping back to the tool, we're going to input our range for criteria 40 to 60. It's a target criteria, and then our justification is just we need at least half of the area to be high marsh. So now that we input all of that attribute information, we're going to start looking at the violation summaries. And again, the tool automatically computes those out. And for the vertical position, the metric for today, our current value, we're doing good. We get no current violations, so we get that green 0 because our 0.804 falls in between 0.8 and 1. For tomorrow, however, given that elevation is changing 1 to 2 millimeters per year, and sea level is rising approximately 5 millimeters a year, you can already see that there's going to be some trouble there. So in the next 10 years, our new criteria range would be 0.85 to 1.05, but the marsh elevation would probably only be somewhere between 0.814 and 0.824. So that's going to throw our trajectory violation. And because we get that trajectory violation, it is going to flag the overall attribute as violated. So we're going to have that red 1 for our attribute status. So for our next attribute of biology, again, we're in good shape currently. That 57% falls between our 40 and 60, which is great. So we get a nice big green 0. But tomorrow we didn't have any trajectory information. This probably is going to happen quite a bit, that we just don't have certain types of information. And the tool still will work. It will highlight the fact that we don't have that information and maybe we should go back. But for this example, we simply don't have it. And so we're not going to get that attribute status, but currently we're doing good. So as we go through the summary, you'll see that, this gives you an opportunity to find that data and to really consider whether or not that data is important for the overall assessment of the site. So here's our output summary tab. It's a little complicated. There's a couple tables that they're just meant to summarize things and help you navigate all the different attributes information that you put in. But what I'm going to do, I'm just going to draw your attention to table 2. We did see that we had our trajectory violation for the vertical position. So that in table 2, we have a big X in that location, and we also have those associated attributes for continued monitoring. So that's just a list of things that are possibly related to the vertical position that we could probably go back and make sure that we have all the necessary information with those related attributes to make sure that we're getting that full story. And so for this, we did have biology and hydrology, and we did look at biology, but we didn't have that trajectory information. So that's kind of a big hole in our overall assessment. And so when we look at table 3, which just again categorizes all the violations that we did or did not see. At the very end of that, we'll see our status that I sort of made a crazy star thing over. And what the tool outputs is that FER, which is further evaluation recommended. So this gives you a moment of pause to go back and say, all right, we probably need to find more data, whether it be with new attributes that we haven't looked at all yet, such as hydrology, or to add information to attributes that we might have already inputted data for, such as biology. And again, for biology, we were missing that trajectory, so that might be an important piece to add. So almost finished here with the onslaught of information. But finally, so now that we're finished that example assessment, I think it's really important to circle back to those goals and figure, answer the question that you originally posed. So, our original concern was this decreasing breeding habitat of salt marsh sparrows. And the question that we asked, did we observe these decreases in breeding habitat? And what the watch tool kind of suggests is that we did find that future elevation was likely going to be a foundational issue at this site. We didn't see anything currently wrong. And as the eBird output, people are seeing salt marsh sparrows here now, which is great. But within the next 10 years, this site might have an impairment that means that breeding habitat is in jeopardy for the salt marsh sparrows. So last slide. I like this phrase, data to decisions and opportunity to need, because I think that I hope that the watch tool sort of supports that, these two ideas. That there's, a lot of restoration opportunities that we're seeing in the area, across the mid-Atlantic. And it's going to be really important to start matching those opportunities to where there might be evidence of need. And that evidence is really data centered. So finding that data and matching the opportunities with the evidence of need is an important next step. And I also wanted to reiterate that the watch tool wasn't designed, we did not develop and design the watch tool to be the one tool for all. We hope that we can use other data sets and other tools to wrap into the watch tool so that we're more organized about our thought processes here. And then Jordan is going to talk a little bit later about how maybe the crosswalking with other tools to figure out how vulnerability functions, or how vulnerability can be categorized amongst multiple sites, and how the watch tool can be used collaboratively with those other tools. And lastly, I just want to put a plug in that a community of practitioners best supports these efforts. We really need to figure out where there are data gaps, and we hope that the watch tool helps support communication about those data gaps and what worked for restoration and vulnerability assessment, and then probably most importantly, what didn't work. So I think that's all I have for this. I don't know where I sit at time, because I'm a fast talker, but sometimes I go off in a tangent. So I'll lean on Caitlin to let me know whether we have time for questions.
Yeah, Leanne, we're definitely good on time for some questions, and there have been some that have come in. One that was answered already, but I just wanted to draw attention to. The question was, does Watch provide default info if you don't have site-specific data? And the answer that B gave was no, but you can possibly find what you need from the professional literature or other tools that exist. And again, we are going to hear about some of those tools later on today, so stay tuned for that. A second question, Leanne, and again, any panelist can answer, is how does Watch deal with areas undergoing natural habitat transitions due to sea level rise? They will likely have violations per the Watch evaluation, but do we need to do anything about it?
That's an interesting question. And I will say, Josh, please chime in, but I'll give it a first go. I think that all of the watch tool output depends on how you're approaching the situation and whether or not the user feels that the transitions that are occurring fall outside of the criteria values that you set. For this breeding habitat example, we were specifically focused on high marsh. However, those same data values would be a problem if you were focused on low marsh. So you can sort of set, your criteria to tell that story in that way. So for that, I think that that's the flexibility that we're talking about.
Right.
I might have answered that.
Yeah, I think in one thing I would just add to that, I agree with that. It's how you choose your criteria data, and also choose your trajectories as well, because if there is a transition area that is developing that maybe would receive say a biological violation, because the biology while under transition is not at a state where we'd want it to be, if we look at, say, vertical position, and we see that this transition is part of an elevation growth, we have trajectory information on that, and we see that although maybe the vertical position's a little low now, it's on a positive trajectory for the future. And this is where it comes down to interpretation. And again, this is a conversational tool. If I was to see that I had a vertical position that was on a positive trajectory and is getting better, and the biology is not doing well now, but I don't have any trajectory data, I may want to wait and see what happens to continue evaluating that metric. So, you know, like all models, you can get out what you put in. You could put in a bunch of numbers that say you have a problem here, there, and everywhere, but it's really once you go to the reflection tab and looking at them all together and having conversations with other people that are experts in this area, where you really start to see, you know, is every output legitimately a concern, or should we reevaluate it? Am I choosing the exact right metrics for this and the ranges, as Leanne pointed out? So again, I think that would be a conversation point to have, especially if you see that this is a transition area and whoever the stakeholders are may be supportive of that sort of transgression.
Yeah, and I think there's a follow-up question to this conversation. Would you need to run multiple different runs of watch to evaluate questions like these?
I would say, I mean, you can. I think the watch, you can, there's multiple lines in each attribute, so you can even compare metrics. So those metrics can be, you know, for two different scenarios. And, you know, to be able to compare the two lines, I think would be important in this example. But, you know, again, that's up to the user.
And that's going to be part of one of the interpretation examples that I give a little later. You're getting, you know, divergent outcomes from different metrics. What do you do with that? What does that mean? So we will discuss that actually after the break.
Awesome. And there's been some active conversation around NOAA tidal data and datums that are old being used and how they need to be corrected for sea level rise. So I didn't know if either of you could comment on that for the group.
Yeah, I mean, some of the datum is changing, and I that's undeniable at this point. The datum that is on the NOAA website is, you know, our national standard at this point, and I think that you know, being consistent with NOAA and what they're, you know, recommending to use is probably good, just for ease of communication. But that's not to say that you don't have, you know, you have to use the NOAA datum within the tool. You can make your own datum. You can truncate NOAA records for the most recent 19 years and create your own datum off that if that's what you choose to do. We don't have specific methodologies right now in the WASH tool to do that. You know, there are other resources available, but the WASH tool doesn't preclude that at all. And so for that, if you wanted to update datum and use, you know, more recent datum, that's possible.
It's always that balance of providing flexibility, but providing direction on a path forward too. So choosing that type of reference data, you know, yeah, I mean, if you have water level loggers out and you can create a good tidal datum for your own site, you can absolutely do that. The burden is on the user to supply their data. And then there's a spot where you can talk about why you did that. So when that comes up in the future, or those conversations happen, it's all noted there. But, you know, at some point, you know, and I guess that point is now, we're all beholden to the data that's available when we're comparing things. So how do we deal with that? You know, what sort of ranges and values do we choose that think best reflects the situation at hand and how they're changing? And running into these issues in a standardized way sort of gives the platform for some of that conversation to evolve. And also people figure out very good ways that they're happy with working around some of those inconsistencies in some of the larger available data products. You know, within a community, there's a place to talk about that. So again, that flexibility in WASH to use what you want, I guess, puts the burden on you to decide what is best and then justify that.
Right, absolutely. And For those of you participating in breakout sessions, you know, we may get into that a little bit more if you have questions about that as well. So looking forward to seeing some of you there later today and tomorrow. For now, I think that concludes our questions. So we are going to take a quick break so you can stretch your legs, grab a glass of water, but we will reconvene at 11:05. So please join us then. We will start back up at that time. So we will see you soon. Thank you, Leanne and Josh, for your answers to the questions. All right, everyone, we are going to get started back up again. We do have 2 more presentations today as part of our agenda. Before we jump into those, I just want to make sure we have most of you back with us today. So I am going to launch a poll just to see if you all are here. So the poll question is, are you back from the break? Yes, I never left, or yes, you're back and you're ready to hear more. Just give it a few more seconds here just to see how many of you have returned. All right, it looks like most of you are back and ready to learn more about Watch. So thanks for rejoining us after the break. I am going to turn it over to Josh Moody, who's going to talk about some investigative techniques and outputs of Watch, diving a little bit deeper into the tool and how to use it to evaluate projects. So with that, Josh, take it away.
Okay, thanks, Caitlin. So, you know, output evaluation, you know, this is always a common question. There's a lot of, you know, tools and statistical models you use. You can input a lot of data and then you get a result, right? And, you know, there's a real skill in how to interpret that and what to make of those outcomes. And I think there's been a lot of value in a lot of these questions so far. You know, there's questions around how we're collecting our metric values, what we're comparing them to, where we're getting trajectory data. And these are all very valid and real concerns that a lot of us deal with every day that there's not a simple answer for. I mean, you know, we're not bakers. You know, you follow the recipe, you know, put these things together, you know, you set the oven, boom, you got a cake. As long as you're not in Denver, it's the same cake every time. You know, that's just not you know, it's not that easy for us. This isn't bench work. We're dealing with dynamic environments that exist at different locations on the landscape that are, you know, being affected to different levels by sometimes the same conditions, sometimes by different conditions. So when you try to impose a sort of standard way to look at things or a standard way to evaluate something upon a dynamic landscape, it's extremely difficult to do. And with that, you know, comes that weighing of the flexibility and the procedural certainty that we're trying to do here. And with Watch, you know, the burden again is on the user to make some decisions, to catalog those decisions, to put that information together. But when things come out, you know, what do we do with that information? So that's what this section is going to be about. After this slide, we're going to move into Watch, and I'm going to go through some scenarios in a few of the different attributes that get at this. So there's a few different concerns. I think a lot of these have been touched upon in the questions so far. again, those outputs are dependent on the inputs. Do we have confidence in our metric of choice? How do we select the right metric that they're getting at? What are our time frame considerations? We're going to get violations here and there. Does that mean, grab the shovels and the hose and run out there? I mean, there's ways that we can explore these data more than just taking the end result. Selecting the appropriate criteria. This has come up a number of times so far. But also want to touch on these global attributes. Soil condition is the example I'm going to use today, and water quality is another one. What is the point of having attributes if they don't, contribute to a deficiency detected? And there is a reason that they're there. So that's something that we're going to discuss today as well. So the first one we're going to talk about, we're going to go into the biology tab, and we're going to talk about confidence in our metrics of choice. So, let's say we're interested in a particular salt marsh habitat, and yeah, how is it in a state where nesting birds are really going to utilize it? So one thing I do want to show is that with vertical position, we didn't have a lot of options for metrics, and that's different in biology. There's a lot of different options here, and so for vegetation productivity metric, we're going to have a lot of method options: below ground, above ground biomass, percent cover, stem density, satellite imagery. And those options are going to change as we choose different metrics. Habitat, percent habitat composition, percent nuisance species, percent high quality habitat. These are all listed in the user guide. Focal species, species of interest that we're in, presence or absence of threatened and endangered, presence or absence of invasive species. So there's a lot more options here of metric choice, depending on what it is you're interested in. But here, let's say we're interested right now in this particular organism likes, some certain density of vegetation. So you're going to start off using a percent cover method to get at your vegetation productivity, which is going to be relatable to, how good this habitat is for this particular organism to nest there. So you go out and you get your, currently our percent covers at 60%. You develop your criteria metric. Maybe you get that data from 5 local sites where the habitat is being utilized. You get a range here, say from 40 to 80%. You've been monitoring this site for the last 5 years. Lucky you, you've got some really good trajectory data. You're seeing a decrease in about 1/4 to 1/2% per year, and you're looking 5 years into the future because really that's how long you've been monitoring, so you're comfortable with that. And you're going to, your forecasted year is going to project your metric forward. It's going to compare it to your criteria range, and lucky you don't, everything looks good. Okay. Units must be consistent. I see an error message over here. So there's my unit error. If I change that to percent, and then my unit error goes away. Okay, so there's no issue there. That's great. But from a conversation with someone at a meeting, is percent cover really the right metric that I want to use? And this kind of gets at one of Doug's last question. So maybe it's not necessarily the cover, because as the plants grow, even if the density gets lower of the stems, the percent cover can make up for that. The existing plants will have enhanced productivity. So maybe it's actually really stem density. Is that really the right metric? So again, you can go out, you've been looking at this site for a long time, and you can count your current or most recent metric. You can compare it to criteria that you have from a regional synthesis paper. You've been monitoring there, so you have your trajectory down. You're going to project in the same time frame. But this, when you go to compare your forecasted metric to your criteria, well, you know what, you're okay today, but you have a trajectory violation tomorrow. And this sort of gets at Doug's question here. One, can you look at a different metrics together? What does that result in and watch, and what do you do about it? Well, the first thing it does, again, this is, a burden on the user tool to decide, which metric is really most informative. For me, who in terms of organisms who specialize in shellfish, I would probably go to the U.S. Fish and Wildlife Service and have a discussion with someone who specializes more in this to decide which sort of metric is, more appropriate. But this format, having these multiple rows here, gives you the options to test these side by side. And when you have options to test multiple metrics side by side, you can start to increase your confidence. When you're really just looking at one value, it's hard to have a lot of confidence in this. But if you're starting to test multiple metrics side by side, you're seeing similar results that can help increase your confidence. When you see discrepancies among them, this non-conformity, that's where you can decide that, all right, I think we're going to need to have a further discussion on this. Well, how does Watch handle it? Well, Watch again is going to assess the level of evidence you provided that there's an issue. Here, using two rows together, you have provided evidence in one row that there is an issue, that your future state is not going to meet the criteria that you have defined for it as being acceptable. So in Watch, in the output summary, you are going to get, here it is, a biology trajectory deficiency. It's going to catalog this. You could have 4 rows, completely green, no deficiency detected. If you have one where there is a deficiency detected, it is going to catalog that a deficiency was detected. So again, the more metrics that you can evaluate side by side, the better, the more alignment, the more confidence you may have. But this might also give you the point of view that, for a particular metric, maybe you need further consultation, which in, salt marsh evaluation is a very good thing to always do, which is to get further consultation with people who maybe specialize in these areas. So the next I guess, question I'm going to look at is going to be this time frame issue. Can we use Watch to evaluate these different violations in terms of their time frames? I'm going to use the horizontal position attribute here for that. Like vertical position, horizontal position is really a singular metric. It's the shoreline position, but there's multiple methods to use to assess it. So this is actually data taken from one of the examples in the user guide. So like Leanne stated as well, I encourage you to take a look at those. And the second example starts to augment the data and change the data around in various iterations to highlight some of these specific issues that may arise and what a user can do about them or how do they go about interpreting them. So for this particular metric, we have a width of a marsh now that's about 100 meters. It's an average distance, from a variety of transects that bisect it. Now we want our criteria here is 75 to 100 meters. And we have that, our high is the width of the marsh right now, it's 100 meters long, but we've done some modeling work that says the water is going to end up on the road if it's not at least 75 meters wide. So that's our criteria metric. We have a trajectory rate of marsh loss of a decline and erosion rate of 2 to 4 meters per year. A lot of erosion. We've gotten this from a variety of local marshes, all facing the same direction. And maybe we just use some more of an accessible platform like Google Earth to measure something like that. We're going to project out for 10 years. Maybe we're the city and we're getting our budget together for the next 10 years. And do we need to allocate money for this? So this is going to project our metric out. It's going to be, either somewhere between 60 and 80 meters wide. So we're going to see a trajectory violation. We need it to be at least 75 meters wide. There's a chance it could be 60. So that's going to give us a violation. So how worried do we have to be? Well, we're looking out 10 years. Maybe we want to see, maybe it's a tight budget this year, usually is, right? So maybe we want to see how concerned we really want to be. So we put in 5 years and well, no problem in 5 years. We maybe go to 7, go to 8, and then we go to 9. And so we start to see the trajectory violations start to happen in 9 years. So, is this an imminent problem? I mean, and that's really going to be up to the user to decide. If the answer to that question is, listen, if we're going to do anything, we can't have that road flood 9 years from now. If we're going to do anything, allocate any money, it happens today, then maybe that's enough. But maybe it's not. And maybe what you want to think is, okay, you know, this trajectory data that we got, maybe it's not the best resolution. Maybe we have some time to get some better trajectory data from our site. And reevaluate in 5 years when we move forward. So we can use this this projection time frame here to start to evaluate, you know, when it is that we need to be concerned about different metrics, different violations we might be receiving. So another one is selecting the appropriate criteria, selecting appropriate values. I'm going to walk through the hydrology tab here. Just to give you an idea of what's in here, we have a couple different metrics. We have hydrologic manipulation, and in there you're going to see things like percent area with restricted or manipulated water flow, restriction extent, percent time flooded. And then we're also in drainage, you know, going to see drainage capacity, percent of open water on the marsh. So a few different options for metrics there. And again, you can refer to the user's guide and additional references in there to look at those a little bit more closely. But again, to walk through the example, you know, we have a value that the marsh is, you know, flooded 35% of the time. Maybe we're pretty confident in that. We got that from an array of water level loggers that we deployed there. The criteria we're going to use is that we want it to be within 31 and 37% of the time. And that's from maybe a very specific report. That's very local and has evaluated a good quality reference marsh. We have our change in we have our trajectory percent change. That's from water levels calculated from NOAA tides and currents, depending on your confidence there. We're going to project out into the future. And what we're going to see is our projected metric. Our metric today is okay, but our projected value of percent time flooded is going to be between 36 and 40. So it's going to be outside of that criteria range. So therefore, we're going to get a trajectory violation for the future. But we want to think when we get those about how confident we are in our values and where we got them from. So this is just a generalized example just to keep things easy. But, you know, if we're going to use a fairly narrow range here of 31 to 37% time flooded, you know, that might come from a local reference marsh. Is that really the entire range that's available? You know, we know with vegetation, there's idealized ranges where you're going to see the best productivity, but there's also ranges that the different vegetation types can exist within, even if it's not ideal. And now if you select narrower criteria ranges, which is probably a little bit more reflective of idealized ranges, you know, it's going to be a lot easier to violate. So when we think about each particular metric and we think about the criteria data that we want to put to this, we want to know how confident we're going to be. Is 31 to 37%, even that's what existed at our reference marsh, is that even realistic for a lot of the marshes in our area? You know, in the areas that we live, a lot of the marshes are impacted to some degree in some way. So attaining an ideal criteria, although it may be textbook, a good criteria, is it a realistic criteria? So when you start to look at maybe wider ranges of values that could be coming from a regional synthesis, could be coming from a wider range of sites, or reflective of the real on the ground conditions that are achievable through there. When you start to broaden those ranges out, if you start to see that the violations are not occurring anymore, that's now a place for conversation. That's a place to consult with local experts. What should our targets be for these sites? What can we actually achieve here? Now, this is actually going to be very informative in terms of team building if projects are going to move forward. It also brings up the question that this isn't necessarily just for our criteria range. You know, I've brought up using the means of values, but maybe in certain cases, if you're going to, you know, look at the elevation of a salt marsh, is the mean really reflective? What if, you know, 70% of the area of that salt marsh is really within a much narrower range that isn't quite reflected by the mean? Is the mode a little better? Is the median value better? You know, when we look for these single values that are going to represent a large area, we're given a conundrum. How do we take something complex and distill it to something simple? And again, those choices are going to be put on the user. Are we using means? Are we going to maybe use a lower threshold? We're so concerned about this particular metric that I don't even want to think about its state as the average. I want to think about its state as the lowest representation here. And again, these measurement justifications are going to give us those places to sort of document that thinking. But that thinking is important, not only in terms of that criteria metric, but also in terms of that current value. Are we making the right selections that are reflective of the urgency we feel and the stakeholder need around the site? And then the last one I'm going to move to is the context of the global attribute, soil condition. So soil condition is a very different tab from the rest of them. So we worked with Rob Tunstead on this one for a while. And, you know, how do we build this one out? How do we assess these soils? And how do we, you know, sort of integrate that? And how does this inform some of the other metrics? And so based on that work, what soil condition does is it integrates organic thickness, parent material, and decomposition state. And it's going to integrate the three of those together to give us an idea of our soil stability. In this example, it's also going to give us an idea how to contextualize some of the hydraulic issues as well. So in terms of our methods, you know, we're really more interested in the thickness, the parent material. So what we have is our organic thickness. What is the depth? It's going to automatically will convert it to inches for you. You can put in your method. And what it's going to do is it's going to give you a grade of each one of these: organic thickness, parent material, and decomposition state for each one based on the depth. For here, it's going to be for, say, organic thickness. So say you have a deep organic layer, that's going to be a little better than if you have a shallow one. Parent material. Now here's where we get into some drop-down options. So you can refer to the user guide for more clarification on this, but we tried to align the parent material and the decomposition state with a variety of different ways to categorize them. So here we have, for parent material, just the sand, loamy sand, silty loam, silty clay, clay. And again, we have for each one is associated with a different level of stability, a different desired state. Decomposition state, here's where you can see, you can use the L1 levels, the H levels, or just sort of that fibric peat or the different O categorizations as well. And again, each one is going to be representative of a different state of stability or desirability. And what you're going to get from the outcome is you're going to get a suggested soil type that you have there. Again, you are going to want to check that. And also it's going to get you an attribute status, a final grade, A, B, or C. Now, to get a C, to get a low quality grade, you're going to need to have C grades across all three parameters. Same with A, and B is what you get for a mix. C was attributed to those three levels because it's going to indicate very poor drainage and very low stability of the soils. And if you get a C, what it's going to do is it is going to give you an attribute violation. It's not going to contribute to a deficiency detected, but here's how we're going to use this for context. So in the last suite of examples I went through, I've got a deficiency detected here from my biology and hydrology trajectory deficiencies. Okay, so we're going to have a problem in the future coming down there. Well, what kind of problem is this? Is it really, the water sitting on the marsh? It's going to be sitting there for a longer period of time. So maybe we just want to build the elevation up there. Although we didn't get a vertical position deficiency. So, well, what else do we have? Looking at this table, well, we've got this soil condition deficiency. So we've got this vegetation on the decline. We're looking down the road at future ponding, but we've got poor drainage here. So if we start building up elevation, Or we start, maybe we want to think about, if water gets back there in any way, it's unlikely that it's going to drain. There's not just going to be good drainage through the soil. So what do we want to do? Well, maybe we don't want to wait until we get to that excessive ponding state, because that might exacerbate the decline. If we get the excessive ponding and the soils can't drain, that could make things a little worse. And maybe we want to think about hydrologic repair or a hydrologic intervention at a sooner time frame than that. So what this would tell me is what we would want to do is probably give Rob a call and also, start talking to some hydrologists, looking at the site a little bit more closely to think about maybe this is really a drainage issue and the biology is really the symptom of that's occurring there. So those are some of the common questions that come up when we've worked with others on this tool. And again, the scenarios in the user guide are going to walk through quite a few different situations that are similar to the ones I just went through. And I think a lot of this really highlights that, watch does require some discussion, and watch requires some interpretation, and watch hopefully can facilitate some of that discussion. So just to close out and let everyone know what the next steps for Watch are at this point, right now we're currently funded through NFWF Delaware Watershed Conservation Fund. That will close out on the spooky date of Halloween 2022. So in that time, our plans are, one, to add that sedimentation attribute, start working out its nexus to the vertical position of the hydrology, as well as doing some of this field testing and validation at long-term aqua stations and other sites of interest, like, maybe more hardened shorelines like Doug, or urbanized ones that Doug pointed out, maybe like Simeon pointed out, maybe taking just a cursory look at a freshwater spectrum. And so we've established a tech advisory group to do that, which has got a small steering committee with representatives from New Jersey DEP and DNREC, as well as our sedimentation work group, which will be focused really on that attribute. And then a larger evaluation work group that as we make some steps in that effort, we'll be running this stuff by a group of people that will help, gauge how well different approaches are working out and maybe things that we haven't considered. And we're going to want all of your input as well. So with this, as we make any changes to Watch, we've got everyone's email. Any changes to the user guide or Watch, you will be updated with. We will send them to you. As part of this effort, we might be able to move Watch to a web platform. As soon as we do that, we would let everybody know as well. And also, ideas for these validation sites, or, thoughts on Watch itself. If you use it, if you don't use it, what you like about it, what it needs, any of that input over the next year would be greatly appreciated. So Leanne and I and Ellie, you can send it to us at any time. But we will probably follow up in early 22 with all of you to ask if you've had any experiences with Watch over the last year, let you know how the development is coming under this funding, and maybe get a little feedback of things that we can consider. I'm just going to answer a couple quick questions from Bill. How's considering a list of definitions and terms used? If you go into the user guide, everything is defined in there. If we are not, if something isn't, and it should be, let us know, and we will most certainly make that update. Brian asked from Delaware Bay program, can we customize it with our own drop-down standard metrics to compare to sites? Right now, it is not customizable, but as we move to a web-based platform where you don't have this singular spreadsheet, right, that you've got to email out to people or they have to come download, there may be more options to make it a little bit more customizable. So ideas like that, Brian, are really things that we're looking for. All of these questions and suggestions are going to be cataloged. So, that could be something in the future. Right now, most of the cells are locked except for the places that you enter data, just so you don't delete some of the calculatory cells. But yeah, I think moving forward, we will try to figure out again, where's that, where we're trying to find that sweet spot between flexibility and providing direction, also providing, maximum customization without, really reducing the ability of it to perform the work it was designed to do.
Awesome, thanks, Josh. There was one other question I think you can probably provide a quick answer to. Is there a future expectation by the regulatory agencies where the use of watch will be required for a marsh project?
Not that I'm aware of. I mean, I don't have any expectation of that. And I've not, yeah, I wouldn't think so.
Okay, great. All right, so we are gonna turn it over now to Jordan West with the US EPA Office of Research and Development. We're really glad Jordan could join us today. And Jordan's gonna tell us a little bit about watch alignment with other tools and just highlight other resources that are out there for you to use. So take it away, Jordan.
Wonderful. Thanks so much, Caitlin. And hello, everybody. I'm Jordan West with EPA's Office of Research and Development, and I'm representing our team that also consists of Jen Stamp and Anna Hamilton of Tetra Tech. And we've been working for a number of years with PDE, especially Leanne and more recently Josh, on some of these tool connections. So I'm going to give you a whirlwind tour today about using some other tools in concert with Watch. I have 3 example tools: the Relative Wetland Vulnerability Framework, the Causal Analysis Diagnosis Decision Information System, and the Adaptation Design Tool. And then I'm just going to spotlight a little bit this little project we've been doing to do a closer crosswalk of the vulnerability framework with Watch to see what kinds of insights arise. So here's the Watch tool flanked by these 3 other tools. And I think it's useful to look at these 3 levels of activity that Josh has used in some of his previous talks, because they can help us orient the tools to each other. If level 1 is site prioritization, that occurs at larger scales. And then when you get to the level of site-specific issue diagnosis where Watch sits, that's where you're diagnosing, obviously, the problem. And then you get some insights from that into the issue-specific tactic selection and design. So with these 3 tools, starting with the Relative Wetland Vulnerability Framework, this does provide insight at the level of site prioritization, but it also can inform how you might think about setting your criteria, standards, and trajectories and identifying tactics when using Watch. The Caddis tool over here on the right sits squarely at the site-specific issue diagnosis level with Watch. It could help with more detailed stressor identification and causal diagnosis of the violations that you're seeing. And then this last one at the bottom is the Adaptation Design Tool, which could be helpful in supporting more rigorous tactic evaluation and design. It provides a method for considering climate-smart design considerations for your tactics. In other words, what will work well today and in the future. So I'm going to go through these one at a time very quickly. The Relative Wetland Vulnerability Framework leads the user through a vulnerability assessment method. It starts by focusing on defining the ecological and decision contexts. What are the wetland classification types, in this case salt marsh, that we're looking at, and why are we identifying them? What are we targeting as the valued functions or services? That then drives our looking at what we call attributes that are key to the provision of those particular functions of value. And then the vulnerability is decomposed into exposures and system responses based on sensitivity and adaptive capacity. And metrics are chosen to reflect those. And then at the end, you get vulnerability profiles that can be linked back to your evaluation of management tactics for adaptation, based on that original decision context. So how can this work in conjunction with Watch? Well, we actually did a project with Leanne using our framework to look at 6 large salt marsh areas in the lower Delaware Bay. The exposure factor that we concentrated on was relative sea level rise, and we used the SLAM model to look at the response being change in marsh acreage, the proposition being that many key ecosystem services are correlated to acreage amount, like key habitats or flood protection. So the results of running through the framework can help identify the sites or areas that are potentially suitable for management activities, both now and in the future. And this could help with perhaps prioritizing based on future value where you even want to do a watch application, or if you are doing multiple watch sites, comparing their vulnerability in the future with each other. But when you get to the within site level, this is a close-up of part of the Dennis site, and you look at a specific marsh type, high marsh, consideration of some of these within marsh factors within SLAM could affect potentially how you set your criteria, standards, and trajectories. The CADIS tool is an online application that is designed to help users conduct causal assessments using a logical step-by-step framework for stressor identification. And so it uses a methodology for determining the most probable cause of an observed biological impairment using elimination, diagnosis, and strength of evidence analysis. The website contains a great many resources and tools. While originally developed for and mostly used so far for streams, much of this I think could be transferable to other systems. Provides methods for identifying most likely causes, developing the evidence cases for or against those causes, provides examples of applications, and some important tools, analytical techniques, as well as tools for finding, storing, and displaying relevant literature-based information to build your evidence case. So how this could work with Watch is you could develop a CADIS-style conceptual diagram that includes watch attributes and metrics. So this is an example from a stream, and you don't need to look closely at this, just to know that the orange and yellow levels here are human activities and sources of stressors in your conceptual model. And this would correspond in our salt marsh examples to things like land cover alteration, channel alteration, et cetera. The blue, gold, and white are your stressors and stressor interactions and modes of action. And this would correspond to some of the site evidence of stress that you're seeing in your sites, like channel erosion, marsh elevation loss, et cetera. And then at the bottom here, you have your biotic responses or your ecological effects. And this is where you're seeing your actual marsh biotic changes, vegetative cover loss, loss in plant diversity, et cetera. So by using the CADIS system and tools, you might be able to take a lot of the watch elements we're looking at fall into the site evidence and ecological effects areas, and you might be able to use this method and look at evidence base in the literature to work your way up to understanding stressor identification and stressor interactions all the way up to the sources. And obviously that could be really helpful in helping to identify and design tactics. The last tool I'm going to look at here is the adaptation design tool. This is a structured approach that guides users to apply climate smart design considerations to potential management tactics. There's also an activity that helps brainstorm additional activities that may be needed based on understanding your vulnerabilities. And along the way, you identify and record insights on information gaps and research needs and uncertainties, as well as any insights on sequencing requirements or interactions or synergies among multiple tactics if you're considering using multiple tactics. So how this would work in our watch case is for management tactics you might have under consideration, these worksheets guide you through this systematic process to first look at what we call category 1 design considerations, which are asking how will climate change directly or indirectly affect how stressors of concern impact the system. This can be a stressor of concern that you're trying to manage with your management tactic, or it could be a stressor that could get in the way of the success of your management tactic. This is an example from a watershed where they're using terraces to deal with sediment and nutrient runoff. So this worksheet asks how climate change is affecting the behavior of runoff of sediment and nutrients in terms of direction, magnitude, mechanism, uncertainty, the timing that's happening, and what the implications are for your target nutrients, how to measure them, and how you'll measure success. The point of this is to move on to this category 2, which is basically based on the changes that you've looked at in category 1. What are the implications for the functionality or the success of the management action? How would it need to be adjusted in terms of location, timing, or engineering design? So that you're marching through a process where you're at the end going to have not just a statement of your management tactic, but a description of what it would take to make it climate smart so that you can evaluate your tactics based on their effectiveness, not only now, but to ongoing environmental changes. So that was my super quick tour through 3 tools. And now I want to just spotlight really briefly a little bit more on the relative wetland vulnerability framework and the watch tool. We've been doing a little project to take the same case study, coming back to the same case study that Leanne presented, and doing a bit of a crosswalk between the two tools. So just as a reminder, we looked with our relative framework at the large scale, and based on SLAM modeling, looking at salt marsh sparrow high marsh nesting habitat with the primary threat being sea level rise, and using SLAM, we looked at the relative vulnerability out to the year 2050 of our different sites. And we were able to zero in on Dennis as one of the 2 sites that looks pretty stable and maybe even increasing a bit in marsh acreage out to 2050. I'll just point out at this point that this is a really good example of how the way you, the method by which you decide to set your criteria in watch can really depend on how you choose to do that. So in Leanne's example, she used the vertical component and had a criteria that had to do with the required proportion of high marsh, and she got a violation within 10 years. With SLAM, which uses a bunch of other factors and is looking at just presence of high marsh, you do not get see a big problem out to 2050. So that's just an example of the kind of interpretations that Josh is talking about that will be important. But we want to zero in on this area of interest that Leanne was looking at, where you have high quality salt marsh sparrow habitat. And we wanted to do this conceptual crosswalk between the relative wetland vulnerability framework and watch, just to see how they line up and what kind of insights might come out of it. So for our framework, what we would call classification attributes is really set up in your scenario description, your objective, which is the high marsh preservation, and for the nesting of salt marsh sparrows. What we would call principal factors lines up with what watch calls attributes. And basically, these are the critical, aspects of the system that generate the valued function or service of high marsh. We parse out exposure and response to look at them very carefully separately, and looking at sea level rise again. And then modifiers of this response are can be a variety of things, including marsh condition. And we've just heard quite a bit about how soil condition can be important. So when we kind of line up the metrics for the 2 methods, we can think about all kinds of different exposures. And, as we've seen, sea level rise is built in, especially to the vertical position component in watch. There can be other types of exposures that are either climate mediated or interact with climate. And I believe that watch has the flexibilities to perhaps have some of these other exposures also influence where standards and trajectories are set. And then we have our response metrics. So I don't have time to go into a lot of detail, and we're still working on this just to see what kind of insights that we get from this crosswalk. But the question is whether these longer term vulnerability considerations could affect any of the projected violations that you might see, or affect the way you play around with and interpret the results through different timeframes. So just to look at one last slide here of, just how layering exposures and response info can be interesting in the longer term. Remember that out to 2050, our area looked, under the SLAM model, looked pretty good for high marsh, but we find that, Leanne saw a problem within 10 years, certainly within 30 years, between 30 years and out to 2075, we begin to see significant losses of high marsh in our area. But we actually project gains in these longer term timeframes in the northwest corner here. So one question is, could or should consideration of sea level rise over longer time frames affect tactic selection and design? Or, you proceed with your plan that you would do in the next 5 to 10 to 20 years, but you start preparing for a longer term, maybe management tipping point where you're prepared to switch tactics or reevaluate and be prepared to do that in longer timeframes. Storm surge can be another interesting thing that we looked at. This is just a look at the category 1 storm surge inundation levels based on the SLOSH model, which stands for sea, lake, and overland surges from hurricanes model. For 2020 to 2018, we can see that the effects of storm surge are really extensive over large spatial scales, but inundation depths do vary relative to our area of interest. And, you know, we see our area of interest is in better shape for that than to the south, maybe not as much as to the northwest. And there's some evidence in the literature that storm surge height can have effects on soil elevation and some longer term effects on wetland stability overall. So is that a factor? Could that affect specifically how and where you think about doing things? And then we wanted to look at one of our condition metrics that we used from mid-tram data, which is the 250 meter landscape condition one. And that's basically an expression of how much there is native vegetation and undisturbed soils and no evidence of human disturbance versus a lot of invasives, non-natives, barren ground, and a lot of human disturbance. And at the level of this mid-tram data, you can see some variation in condition. And when you kind of overlay that to the other things that we've been looking at, you could ask whether this could have anything to do with tactic success in your area. And more importantly, you know, if we've identified this northwest corner as being really important in the out years, in the long term, maybe this is a place to really focus on improving condition of this metric and others if they also correspond. So that is my very, very quick run through of ideas. I know it was very fast, but we'd really be interested in what people are thinking about these much longer timeframes, and we'll take questions if we have time. Thank you.
Thank you so much, Jordan. That was great. Great overview of different tools and resources that are out there and how they may be able to fit into Watch. So thank you so much for joining us. There are a few questions and we do have time. So the first one I'll ask is, how is EPA planning on using these tools? Is it for plan support or regulatory uses or other?
So, you know, I'm in the Office of Research and Development, and our job is to kind of support the regulatory offices and support those who are, you know, dealing with the regulatory side with tools that will help them. These are not tools that are requirements. And, you know, as you can see, the three tools that I talked about function at different scales. You know, the relative vulnerability framework is a prospective tool. The CADIS tool is a retrospective tool. And so the main thing we're doing with this project and working with Leanne and Josh to kind of look at these tools around Watch is this kind of endeavor of my Office of Research and Development to say, look at how can we make all these different tools that speak to different kinds of questions and different spatial scales and time scales. Is there a way that we can make them speak to each other or harmonize them in some way that's useful? So that's really the impetus of this project. Based on what we figure out and sort of the insights that we have, maybe that will grow into something that's more of an integrated kind of tool. But right now it's a research project. So love to keep people apprised of what we're doing and get a lot of feedback, just like with the Watch tool itself.
Yeah, absolutely. And I think a related question to follow up to that is, has EPA used a combination of tools like those presented to identify watershed stressors and management responses? And is there a website or location to find information about this?
I have not seen that, and that's why I wanted to do this project. So I would like to do that very thing and produce sort of an assessment of how that can work. And if there's a lot of interest in it, if it looks like it has potential, actually do a real world case study to develop that out and demonstrate it. Because I think we can all agree that there is so much data, so many tools, and how do you identify which things can go together and enrich each other, and then how do you actually use them? It's actually not easy at all. And so that's part of this exploration is I gave you a quick talk about how it would work in theory, but actually doing it is extremely complicated. So that's one of the things we're interested in exploring with the project.
Yeah, absolutely. There is another question that just came in. Can pollutants such as heavy metals be modeled in the water chemistry tab? That might be for watch. I'm not sure if that's for the other tools you mentioned.
I think that would be for Josh.
Yeah. So yes, you can, again, for the, in the watch tool, what you're going to do is you're going to set criterias and, see if you surpass these criterias now or in the future, as if you have trajectories. So you can look at a variety of the different water chemistry. Watch is not necessarily going to evaluate how those might change over time. It's just going to respond to the data it's given, concentrations, changes, thresholds, things like that. And, if you surpass any of your defined criteria, it will give you a violation. That will not contribute to the site-wide deficiency, because really things like soils and water chemistry exist at scales outside of the specific site. And if honestly the end goal of watch is going to be, decide if we do have specific issues, how do we approach the next step in doing something about those issues? Working on a specific site is usually going to exist within the context of things like soils and the surrounding water body chemistry. But those are important things to know, because they're going to influence potentially the success of any sort of intervention effort on those sites. So, water chemistry is going to be another tab we're going to dive into a little bit more. You can look at a variety of things, and I think it has the longest list of metrics of any of the tabs, but it does approach them in a similar way.
Great, thanks. And just one final kind of bigger picture question, I think that both Jordan and Josh can answer. In the example shown today, we've seen 5-year, 10-year timeframes. Should there be more focus towards a small handful of options like 5, 10, or 50 years? Otherwise, there could be difficulty in comparing results. So just any thoughts from you, Jordan, or from any of our panelists on that?
Jordan, do you want to speak first, and then maybe Leanne?
Well, I think Josh, the examples you showed of kind of playing around with the year up and down to see when a violation, appeared is a really interesting way to go. I think there's, like you've said, there's a burden on the user to, be careful when using watch to use the same units. And it's also going to be a burden to, I think, deal with this time frame issue, because I would not want to lock it into to only a few intervals, because then because I think a huge part of it really is going to be playing around with the metric combination, playing around with the time scale, and thinking on both shorter and longer time frames. So that's just my feeling about it. You go ahead, Josh.
I'm going to agree. I mean, a lot of the purpose of watch is exploratory, and a lot of our confidence in projections are going to be based on the trajectory data that we've collected. How comfortable are we projecting, 30 years out from a 5-year long data set? So I think right now the state that watch is in, it has the option to enter any sort of years you want. You can enter 30 years, you can enter 20 years, you can enter 1 year, you can enter a variety. Some of the other tools that are under development now, especially ones that are using some of the more defined sea level rise scenarios and things like that, give more of these static options in terms of the timeframes available for the evaluation. And this is another example of something that I think that's going to be, up for discussion, as watch continues to evolve. Right now, it is, like all tools, they're all a work in progress, and what was important to us was to develop something that could change as available information or a community consensus on what our appropriate approaches change. So I think this will be a question that we'll continue to visit. So, Jordan?
And it just occurred to me, I don't think that it's limiting the ability to compare in any way, because for any example, you can just go in and put the year where you want it to be and see what the result is, right? So all you have to do is change that time frame, and you can compare any example with anybody else's example, as long as they use the same metrics.
Yeah, Jordan, that's a great point. Thanks for pointing that out. Did you have a follow-up response, Josh?
No, I'm happy we're getting all the questions that we're getting, because this is going to be really helpful over the next year as we approach this and think about the flexibility that people want, the flexibility that's best able to be provided, to sort of walking that balance beam.
Yeah, absolutely. And so on that note, I think that's going to conclude the workshop for today. So thank you all for your active participation and all of your questions. I know we would have wanted to do this in person, but it's good that we were able to roll out a training on Watch virtually. And thank you to all of our panelists for your participation as well. If you did register for an optional breakout session, you should have a calendar invite to those with Zoom links. So we look forward to seeing you there to continue conversations about Watch. And then lastly, a survey will be sent out in a few days. So please take a few minutes. It's a quick survey to answer some questions about today's workshop. We do look at every response, and it does help us plan future workshops. So thank you so much, and we hope you have a great rest of your day.
Apparently sent that to you, Caitlin.
It's okay.
Are we going to have a quick
Yeah, we'll let's jump off and go over to Google Meets. Ellie, if you are able to stop recording, that would be great.